So today I will talk about extremal dependence of moving average processes driven by exponential-tailed Lévy laws. This is a joint work with David Bonin, Sebastian Engek, and Dr. Hilder. So in this work, we are interested in the moving average processes, which are also termed process convolutions, and have the representation of this form here, where D is a subset of RD, which possibly can depend on the location S, and G is a measurable non-negative function, and M is a random measure. This is a natural and popular construction for non-Gaussian processes. So often we see that M is the random measure, which leads to a Gaussian process for U. But this can be simply extended to non-Gaussian processes by replacing this Gaussian measure with a non-Gaussian measure. And some popular examples include the non-Gaussian OU process, which has just been mentioned by Neha, and also the type G-10 SPD random fields. I will come back to these two examples later. And why do people consider the SPD-based formulation of Gaussian and non-Gaussian processes? And the reason is that one can use the finite element approximation, which is a classical technique in numerical analysis for solving PDEs. And so this finite element approximation has this linear form. And with this form, we can obtain sparsity in the resulting precision matrix of the approximation model. And so this, the simulation and inference can be done efficiently. And I want to motivate the problem we are studying by a data application. So on the left-hand side, we see the Argo float seawater temperature measurements data in the south of New Zealand. And this data set has been shown to exhibit non-Gaussianity in certain areas. And this has motivated the use of the type G-10 SPD fields rather than its Gaussian counterparts. But the dependence structure of the SPD and the general moving average processes has mostly been studied in terms of their Pearson's correlation. But in climate science applications, we know that the most interesting events are the extreme events. So one might ask, what is the extremal dependence for this finite element approximation model induced by the mesh? And if we use this model for the temperature data, then can the temperatures be simultaneously extreme at different locations? Or one can go further, what if the mesh size tends to 0, and what is the limiting extremal dependence? And these are the questions we want to address in this work. So I have mentioned extremal dependence quite a few times. Here we focus on the commonly used extremal dependence measures. And the most commonly used measure is the tail dependence coefficient chi, which is defined as this limiting probability of one variable being large, okay, when the other is similar large. And we have two different regimes. So when chi is equal to 0, we say they are asymptotically independent. And when chi is bigger than 0, they are called asymptotically dependent. And when we have asymptotic independence, so chi is equal to 0 and it's not informative, we can use another measure, eta, to measure the residual extremal dependence, which essentially captures the decay rate of chi and going to 0. And so in this work, we focus on the exponential tails because most of the examples considered in the non-Gaussian OU process and the type GSPD models have exponential tails. So we say a random variable y is have an exponential tail if its distribution function satisfies this condition here. And some typical examples are the exponential distribution, the gamma distribution, the Laplace distribution, the generalized inverse Gaussian distribution, and the generalized hyperbolic distribution. So the last two examples are the main examples considered in the non-Gaussian OU process and the type G-10 SPD fields. And a smaller subclass of the exponential tails is the convolution equivalent tails. So if y has an exponential tail and further its distribution function satisfies this condition here, so which essentially says that the convolution with itself has an asymptotically equivalent tail, then we say Y has a convolution equivalent tail. And one example is when Y has this type of tails, and it is convolution equivalent, tail equivalent, if and only if lambda is less than 0. So remember that our target is to investigate the extremal dependence of the moving average processes. But this is not straightforward because there's no analytical form of the finite dimensional distribution function or density functions of this non-Gaussian process. So the approach we're taking here is we first consider a discrete index model, and then we use the results of the discrete model to understand the extremal dependence of the continuous processes. And the discrete model we consider here are the linear transformations. So if you remember, this is also the form of this finite element approximation of the SPD fields. And this is why we start with this discrete model. So x1 and x2 are both linear transformations of a random vector y with independent components, and have exponential tails with the same index beta. And the coefficients aij are non-negative. And it turns out that the extremal dependence of x mainly depends on the largest coefficients on the first row and on the second row. So if we denote the index sets corresponding to the largest coefficients on the first row and the second row by these two sets, and their intersection is empty, then we get asymptotic independence. And if these two index sets are equal, then we get asymptotic dependence. And you may ask, why do we have these results? The intuition behind this is that suppose that A11 is the largest coefficient on the first row, then the tail of x1 would be determined by the tail of y1. And similarly, if A21 is the largest coefficient on the second row, then the tail of x2 would be determined by y1. In other words, in this case, the tail of y1 would determine both the tail of x1 and x2. And this is why we get the stronger form of extremal dependence, so the asymptotic dependence. And otherwise, we would get asymptotic independence. And some more details about this result. If these two index sets are equal, then we can show they are asymptotic dependent, and we can compute the tail dependence coefficient chi in this form. And furthermore, we can show that the residual tail dependence coefficient eta for this model can be computed with this formula. And we can show that if these two index sets have an empty intersection, then eta is strictly less than 1, and x is asymptotic independent. And some remarks about this result. So clearly, we have another boundary case when these two index sets are not equal and their intersection is not empty. Then we have eta is equal to 1, but we need more assumptions to determine whether chi is bigger than 0 or equal to 0. And this result of the discrete model is of independent interest because it gives an tractable way to bridge asymptotic dependence and independence by simply varying the coefficients in the model. And so here we have studied the extremal dependence of these linear transformations, which can be viewed as a sum model. And this result can be transformed to a product model. So if we assume that yi bar IID with absolutely continuous distribution function and regularly varying tails, then the product model, this model has the same extremal dependence structure as our sum model if we consider yi as the logarithm of yi bar. And now let's move on to the moving average processes. So to describe the extremal dependence of this continuous process, we need some working assumptions on the kernel function G and the random measure M. So we assume that the function g is non-negative, continuous, and strictly decreasing as the distance h goes to infinity. And we further assume that for any bounded border set B, the variable MB has an absolutely continuous distribution function with exponential tails. And so here we need to notice that for any bounded set B, the distribution function of MB would have exponential tails with the same index beta. And this assumption seems restrictive, but it is in fact a natural result of the convolution closure property of exponential tails. So suppose we have an exponential tail with index beta, and then we convolve this tail with another lighter tail or larger exponential tail with the same index, then the resulting tail would be an exponential with the same index beta. And we consider the case, we first consider the case where the domain of integration D is fixed and does not depend on the location S. And then we consider the integral approximation of this process. So with what we are doing here is we approximate this continuous function G by simple step functions. And then we can approximate this integral with this finite sum. And then we can show that if the assumption 1 and 2 are satisfied and the kernel function G is convex, then as the mesh size tends to 0, the limiting residual tail dependence function would have this form. And now if we consider another case where the domain D depends on the location S, so we consider the temporal domain, and the moving average process has this form here. And similarly, if we consider an arbitrary partition of the temporal domain, then we can approximate this integral by this finite sum. And then we can show that if the assumptions 1 and 2 are satisfied, then as the mesh size tends to 0, so the limiting residual tail dependence function would have this form. And notice that this function here has a different form than the previous function. And now let's move on to the Langaussian OU process. So the Langaussian OU process is defined as the stationary solution to this SDE, and the existence of such process is guaranteed based on the notion of self-decomposability. And this process has the integral representation here. And because of this integral representation, we can show that if the stationary distribution function of this SDE is absolutely continuous and has an exponential tail with index beta, then this process is asymptotic independent, and the result, the residual tail dependence function would have this form. And one remark here is that so if the background driving Lévy process is the classical Brownian motion, then we get the classical Gaussian OU process with a different residual tail dependence function. And so we can say that the exponential tailed OU process indeed has a different dependence structure than the Gaussian counterpart. And so instead of specifying the self-decomposable distribution function of this OU process, we can alternatively define the process by specifying the Lévy process Z. If we consider a partition of the temporal domain, and then we can approximate this OU process by this form here, and under mild assumptions, we can show that if the Lévy process Z at time point 1 has a convolution equivalent tail, then the resulting process UT would also have an exponential tail, convolution equivalent tail with the same index beta. And furthermore, all the increments of the Lévy process would also have the exponential tails with the same index beta. So this means that all the increments here are independent, and they all have the exponential tails with the same index beta. And this is why we can use our our results in the discrete model here. So what we plot here is the residual tail dependence function of the integral approximation of this OU process, and also its limiting form, the black line. So what we can say is that as the mesh size delta goes to 0, so the eta function of this approximation model converges to the true process. And for the type G-10 SPD random fields, it is defined as the stationary solution to this SPD. And this solution can be written as this moving average process form. One remark here is that this function G, this kernel function G here, is convex only when the smoothness parameter alpha is less than or equal to 3. And if the function G is non-convex, we conjecture that this residual tail dependence function has this form here. And now if we come back to the data application, so on the right-hand side, we fix the SPD parameters and we choose the smoothness parameter alpha is equal to 3. And then we can compute the residual tail dependence function of this approximation model, the finite element approximation, and also the integral approximation, which are the blue and the pink points here. And also we can have we have the limiting form. So what we can see here is that the mesh chosen in this data application is quite fine, and the eta function of the approximation models are quite close to their limiting form. And to summarize, so here in this work, we have studied the extremal dependence of linear transformations of exponential-tailed random vectors. And we further used these results to study the moving average processes, which include the exponential-tailed OU process and the type G-10 SPD fields as special cases. And in terms of statistical modeling, the linear transformations have the potential to be useful for modeling extremal dependence because they bridge asymptotic dependence and independence in a tractable way. And this is an active area of research in the extremes community. And an interesting and natural question is whether exponential tails are the only ones which can yield both extremal dependence classes and linear transformations. And that's all for my presentation. Thank you for your attention, and I'm happy to answer any questions.
Okay, thank you, Zhongwei. Do we have questions for the speaker? Okay, I have a question. So, so for linear combinations of regularly varying random variables, so the main paradigm is the one big jump principle. So the linear combination is large precisely because one of the innovations is large. And then in the moving average process, it propagates. So in this exponential case, is it the same thing that happens, or it's different? Do you have any idea?
I mean, in the exponential case, so the tail of x would be determined by the innovations with the largest coefficient, with the heaviest tail.
Yeah.
And in the regularly varying case, so suppose that here all the yi components have the regularly varying with the same index.
Yeah.
X1, so x would also have regularly varying tails with the same index. So the tail of x would not depend on the coefficients a1, I. Okay. And this is why in the heavier tail case, you can only have asymptotic dependence. So you cannot get asymptotic independence. And I mean, what you can get is exactly independence when when x1 and x2 do not have shared components. That's what you get, but you cannot get asymptotic independence.
Okay. Andre, please.
Thank you. Maybe a stupid question, but could moving average processes be extended, say, to autoregressive moving average processes and related types of processes in this case? ARMA and others, and the analysis then proceeded there.
So our results only applies for moving average processes of this form. It's because we can approximate this integral by finite sum. But for the ARMA process, I'm not sure you can write the process as a sum of independent terms. I mean, if you can, then you can. Our results might be applicable. Otherwise, yeah, you might need a different proof technique.